Hi everyone. This week we're going to talk about usable authentication and particularly about passwords. The idea behind usable authentication is that people need to do something to get themselves into a secure system. Generally we do that with passwords, and passwords tend not to be very secure. There's a lot of reasons for this, and I'll point you to some readings in this week's lecture that will discuss that. What we're going to talk about in this particular video is the usability of passwords as we use them now, before we get into some of the alternatives to passwords. This is one of those things that HCI people love to talk about because passwords are so unusable, and actually they don't have to be. You've seen this slide from me before. These are the 10 most popular passwords. None of these are very good or secure passwords, and we'll actually describe why in the next slide. But these are easy passwords for people to remember, and that's the lesson to take out of this. People are picking terrible passwords that offer very little security, but they're picking passwords that are easy to remember. So what that does tell us is that user preference when it comes to passwords is that they're easy to remember. And in fact, if you force people to come up with passwords that are hard to remember, they're either going to forget them frequently, and then they have to reset their password, which is a problem, or they're going to write them down and put them in places that are easy to find, and that compromises the security. Now remember, we combine this with the fact that when we ask people to create passwords, first we give them this huge set of rules: how long it has to be, uppercase, lowercase, numbers, special characters, what characters can be there, what can be repeated, what can't. So this is a very complex set of rules. Already we can tell that this harms the learnability and the memorability of a password. If you have to follow all these crazy rules, it's going to be hard to memorize what you've come up with. On top of that, many systems, including our system at the University of Maryland, require you to change your password every 6 months. I get angry every time I get one of these emails because I have just learned the password that I have and now I have to change it again. Then you're supposed to have different passwords across all the sites that you use. And on one hand, this makes sense. You don't want somebody to compromise one system and then have access to a password that you may use in other systems. And we've seen some of those attacks where people will hack into an e-commerce system where they have people's email addresses in their passwords, and then they're able to actually use those passwords to access people's email, which is extremely insecure and is a big problem. But if you think about having passwords on hundreds of sites, and they're complicated on every site, they're different on every site, and you're changing them every 6 months, that's bad. People can't remember those. And the solution from a usability perspective is not to make people use password managers, is to make passwords more usable, or have alternative authentication schemes. As I said, in the rest of the videos for this week, we're going to look at alternative authentication mechanisms, but in this video we're going to look at how we can have passwords that are easier to work with. There's a reading that I want you to look at on the usability of passwords, and you should look at that before you watch the rest of this video because I'm going to go over some of the things that you will have read about in there. So let's look at some of the lessons from that reading because it does a really nice job of capturing the issue. There are a few ways to attack passwords. You can have a human attack, so this is where you ask someone for their password, you guess their password because you know their dog's name or their kid's name or their birthday. Maybe you go into their office and you know where they might have written it down. Maybe they stuck it on a post-it under their keyboard. These have nothing to do with computers or computing, it's just a human attack. This is actually one of the easiest ways to compromise a password, and we'll come back to this ability to do a human attack later on. Putting those aside though, brute force is an easy and common mechanism to attack a password. In this case, you just start guessing with the letter A, you go through the letter Z, and if it's not a single character password, you go to 2-character passwords. You try all the 2-character combinations, and so on until you hit the password that they've found. There are programs already out there that you can download on the internet that will brute force attack a system. It's a very easy thing to do, but it can take a long time. There are common word attacks where you actually guess things that are commonly used as passwords or that are actual words that are common. And related to that are dictionary word attacks where you just go through the dictionary and try every word that's in there, assuming that somebody's going to pick an easy to remember word. We saw some of these things on that list of common passwords. Baseball was one of them. Password was one of them. That's something that you'd easily get to if you were going through dictionary words. So, taking these as ways that we can computationally attack a password, the article that you had to read looks at how difficult it would be to actually attack a password, to break a certain password. So here's the first chart from that paper. You are given 6 character passwords, and you want to see how hard they are to attack. The method that we use to attack is the one that would be most successful at breaking any of these passwords. So we're kind of looking at the worst case scenario for the user. The attacker has chosen the most successful method to break your password, and we're going to get an estimate of how long it would take to do that. If you're just picking 6 random characters, a common words attack or a dictionary attack won't work. But brute force mechanism would work, and it would take about a month to break the password. That's pretty risky. A dedicated attacker would let some code run for a month. If you pick 6 random characters with numbers and you do a brute force attack, it takes 8 months. Now the reason it takes longer is because if you go through all the characters, you have 10 less options for each of these 6 characters. You have all 26 letters, but you don't have the numbers 0 through 9. And so you add in a lot more complexity if numbers are in there. That would make it take about 8 months to brute force attack your password, and that's pretty low risk. It's possible that an attacker would spend the better part of a year trying to get into your system, but it's likely that they could just go on to someone who has an easier to break password. If you do 6 random characters where you have uppercase, lowercase, symbols, and numbers, the brute force attack is much harder. Now you have 26 lowercase, 26 uppercase letters, all the numbers, all the special characters. So there's much more complexity to guess each one of those letters, characters. So it would take about 219 years. Essentially, you're secure for life. You're going to die before anybody can attack your password. So that's great. If we do a 6-character common word like orange, that's going to get guessed in about 3 minutes, so it's useless. And if we have a 6-character uncommon word, so this is a word, but not one that people normally would use, a dictionary attack would find that, and it would take about an hour and 22 minutes, also useless. So the lesson from this is that passwords are more secure if they have random characters, uppercase, lowercase, numbers, and symbols, right? And that's the thing that we're required to have in all of our passwords. And in fact, a lot of systems require 8-character passwords, so it's even more secure than this. So we should not be bashing IT people for making us have those passwords, right? That's the lesson from here. But actually, no, because a 6-character random character, mixed case, numbers, symbols, password is very hard for people to remember. If I set you guys down to the task of memorizing all of these passwords, which ones are you most likely to remember? Well, orange is probably the first one. Wusa, this uncommon word, still kind of sounds like a word, and that's probably next. These 6 random characters, a little bit easier, and this is by far the hardest. If I had you memorize these passwords and come back in 2 weeks and tell me, orange may be the only one that you remember. So we've created a system here that's secure if we require people to do this mixed case symbols and numbers password, but very hard to remember. Could we create something that's equally secure but is also easy for people to remember? Here is an alternative where, again, we're using the most effective mechanisms to break these passwords. And instead of requiring people to do uppercase, lowercase, numbers, and everything, they pick 2 common words. In that case, it can be broken in 2 months using a common word attack. But if they pick 3 common words, the common word attack would take over 2,000 years to break it. That's secure forever, because there's so many possible common words to go through and to try in combination. But remembering the phrase, "this is fun," as your password is extremely easy for people. So you can allow people to use common words as long as they use enough of them in combination. They remember a phrase then, which is very easy for people to remember, but it's very hard for computers to break, even with the most effective password attack scheme, in this case is common word. On top of that, we could do 3 uncommon words Fluffy is puffy. Fluffy and puffy are not common words, and so a common word attack won't get those. A dictionary attack that would finally hit those words would take 39 million years to break it. And if we do 5 uncommon words, doobie doobie dub, that again is something that's easy for people to remember. A brute force attack would be able to break that, but some of these wouldn't even appear in a dictionary, so you would have to do brute force. And then we end up with this ridiculously long amount of time to break the password. So in other words, if you let people pick passwords that make sense to them, but require it in a way that keeps in mind the kind of attacks that can be used, you can create extremely secure passwords that are also extremely usable and easy for people to remember. Let's take one more example here. One way that password systems are protected is by stopping people after they've broken into a system or tried to break into a system too many times. So if you try to authenticate, and you may have seen this on your banking website, for example, if you enter the wrong password enough times, it stops you, it makes you wait. Having a system that's implemented with a nice amount of time to block people out who are trying to attack it can also make passwords more secure. So if we take Alpine Fun, the password that we talked about before, and we allow people to attack 100 times per second, it would take 2 months to break the password. If you can only authenticate 1 time every 5 seconds, it would take 63 years. Now, 1 time every 5 seconds is an eternity for a computer that's trying to automatically log in, but for a person, you probably have to wait 5 seconds between when you enter your password and when the screen comes up that tells you it's correct or not. So a human is unlikely to notice this delay, but it makes a huge difference for the computer. And if we allow someone to try to authenticate 1 time every 5 seconds, and then after 10 attempts that are incorrect, we put an hour-long block on it, it would take a computer over 1,000 years, almost 2,000 years, to break that password. So the password is the same, but the system can be set up in a way that makes this very easy to remember password actually extremely secure by controlling how many times people can log in. And this seems straightforward, but if you remember, there was an attack on Apple's iCloud system where a bunch of photos of celebrities were put out online. And this attack was allowed because iCloud did not have a block on the number of brute force attacks that could come in. It just let them keep coming. Where a good secure system should have a block that after a certain number of attempts, either the login is blocked or someone is notified, so the attack is stopped. This is a simple thing that doesn't have anything to do with the user, but that allows users to have more secure passwords. This is a comic from XKCD. This is also a signed reading, but all it is this comic that we have in the screen here. And this actually makes the point for us quite well. This is the kind of password that we're making people remember now. You have to pick some uncommon, non-gibberish base word. This is, a hint that's given to people. We'll pick something that's kind of like a word, but mess around with it a little bit. So we put in some numbers and some letters, and we do some uppercase and lowercase. But then we have to have like a special character, and so we kind of stick it on the end with another number, but we don't remember which order those go in. And so we've got a really long password here that has upper and lowercase, numbers, and special characters. And this is about 28 bits of entropy. We can say it takes 2 to the 28th attempts to guess that kind of password. That's 3 days if we allow 1,000 guesses per second. Now, that's a pretty weak system that would allow 1,000 guesses per second, but 3 days is a pretty easy amount of time to guess this crazy password. And it's very hard for people to remember that password. On the other hand, here we have a system with 4 common words. This is even more secure than the examples that we were looking at in the previous slides. And those 4 words together are pretty easy for a person to remember. Those have 44 bits of entropy, even if they're all in lowercase, which would take 550 years to guess, even at that very insecure 1,000 guesses per second. So this kind of password is extremely hard for a computer to remember, but very easy for a person to remember. And here's a little picture of a person memorizing this correct horse battery staple password. So in other words, we've gone through all of this effort over 20 years of people having access to systems that require passwords. And what we've done is create a system with passwords that are actually not that hard for computers to guess, but are very hard for people to remember, when we could create a system that has passwords that are very easy for people to remember, but very hard for computers to guess. So in conclusion, password systems would be more secure if passwords were more usable. And that's true for human reasons and computational reasons. We've looked at computational reasons in a lot of these slides, and the human reasons come down to the fact that if you make people remember difficult passwords, they're going to fail. So they will either reset their password frequently or they will write it down, and that creates all sorts of opportunities for these sort of human attacks on the password. We know we can make easy to remember passwords that are hard for computers to break, and why haven't we done that? Why haven't we seen systems implementing these long, complex passwords that are actually common words that are easy for people to remember? Honestly, it's because the security people probably are afraid of going that route, even though there's the math to prove that it's good, and it's difficult to change the status quo. So my charge to you, dear students, is to go out there and talk to people about usable security and convince them that having easy to remember passwords can be even more secure than our current 8-digit hard to remember passwords, and that's something that we should get on. In this video, we're going to discuss two-factor authentication, what it means for authentication security, and what it means for usability. So just as some background, two-factor authentication, which I'm going to abbreviate as TFA in the slides just for brevity, basically means that you have a password combined with a one-time unique code. So while people can guess your password, they can't guess your password and this unique code, and those two things together are designed to make the system more secure. That unique code can be generated in a number of ways. Sometimes you have a device specifically designed to create that unique code, and we'll take a look at an example of one of those. That unique code may be emailed to you when you need it. It could be sent to you in a text message, or some places like Google actually have an app that's designed to generate that code for you if you want. Let's look at a couple examples of these two-factor authentication codes being generated, and we'll start with one generated by a device called an RSA Secure ID key. This is an RSA Secure ID USB key. You can see the little cap on the right-hand side that covers up the USB. And in the middle is a digital screen that generates a unique ID that's used in two-factor authentication. If you watch, you can see the number in the middle keeps changing, and on the left-hand side of that digital display is a set of bars that count down the time that number's valid. What we're seeing here is this video sped up almost 6 times its normal speed, so the numbers actually stay visible for quite a while. With this key, I use it to log into a consulting job I have, and I'll type in my username, I'll type in my password, and then I will append the 6 digits from this RSA key onto the end of my password, generating a one-time unique password. There's a unique identifier for my particular RSA Secure ID key that we're looking at here. That's linked with my account, and the numbers that are appearing on my key are linked to the ID of my key, which is linked to my account. So someone else with a different Secure ID key would have different numbers showing up. They couldn't just use the numbers on my key to log into their account. So there's a lot of security going on here. I have my unique username, it's connected to my unique RSA key, I have my password, and I have the temporary number that appear on my key only. I combine those together in order to get a unique password. The next example we'll look at comes from Google. They have two-factor authentication available for Gmail and other applications. This video is actually taken from Google's description of how their two-factor authentication works, and you'll see how they can generate this unique code either through a text message or through their app. And in addition, we'll actually see how the two-factor authentication login process works on Google, and in fact this is how it works on a bunch of different sites.
After you sign in with your username and password, Google will ask you for a verification code. If you chose to receive a text or voice message when you set up two-step verification, Google will then send it to you on your phone. If you're an Android, BlackBerry, or iPhone user, You can also choose to generate a code on your phone using the Google Authenticator app. Enter the code from your phone. If you trust this computer, you can check this box and you won't be asked for another verification code for 30 days.
So, how does two-factor authentication help security? Well, it's definitely more secure because you have two things that a hacker needs to get into the system, not just one, and it stops most hacking attacks because that unique code is constantly changing. So even if they were able to get a hold of it once, they can't get a hold of it multiple times. And if they want to get a hold of that, they generally need to access a device that you have, your RSA key, your email, or your smartphone. Users also perceive two-factor authentication as more secure, so they understand that there's a couple extra steps that's making the system more secure if they use it. But how does it affect the usability or the perceptions of usability? Research says that two-factor authentication is actually much less usable than traditional password-based or single-factor authentication. It's definitely slower. Measurements of speed show that it takes more time. User preference also indicates that it's less preferable and less usable in a number of ways. Users felt that it was less usable when they were asked. They thought it was less convenient than doing single-factor authentication, which makes sense. You have to have a device or access to your email in order to log in with it. And they felt it was harder to use. So overall, users didn't really like the usability of two-factor authentication in research that studied it. It's slower, which is another measure of usability. So we get a big loss in the usability department when two-factor authentication is introduced. There's one simple conclusion from this. Two-factor authentication is more secure but less usable. That doesn't mean that we need to take it out of systems. There are some systems that are very sensitive. They need the highest security possible, and that means including two-factor authentication. But the fact that it's less usable means that it shouldn't be relied on as a way of simply making systems more secure, because users don't like it, and that means that they're going to have trouble using it, and if given the option, they're likely to turn it off. In this video, we're going to look at biometrics. This is a type of authentication that you probably have seen in movies where people have to scan their handprints or speak into something or have their eye scanned. And until pretty recently, movies were almost the only place you saw biometric authentication. But mobile devices have brought biometrics into the modern space where now people use them every day to log into their smartphones. The examples that we're going to look at in this video are all based on mobile devices, but in fact, biometric authentication can work in any system where you need to uniquely identify a person. So biometrics deal with using a person's biology to identify them. We look for unique traits that will distinguish one person from another. So that could include a fingerprint, a scan of their eye, things like facial recognition, or even voice prints. We're going to look at some examples today of how that's actually implemented and how well it works, and how these types of authentication mechanisms affect the usability of logging into a system. Without biometrics, users log into their devices either with a PIN, which we've seen, or using a password. This can be frustrating. In fact, it can be so frustrating that sometimes people just turn this kind of authentication off. Biometrics can make it easier, and we're going to look at a few examples of biometrics that are already in place and available on mobile devices. Let's start with fingerprint recognition, which is something, again, that we've seen already used, and so we'll just look very quickly at this working again. Facial recognition scans a person's face and identifies important points that everybody has on their face. That includes things like the corners of the eyes, the tip of the nose, the edges of the mouth, and so on. The distance and proportions between these points are unique between individuals, and so you can use that to identify people by taking a picture of their face and scanning it. Let's look at as an example of this in an app that's used on the iPhone where you can use facial recognition to lock away files. Voice recognition uses patterns that everybody has in their voice. These are things that we can't consciously control. So it's not necessarily just our pronunciation, but it's our tone of voice, the pitch, the timbre, and so on. Again, here's another app for the iPhone that uses voice recognition to allow access. One 637 7361. So we've seen some of these different ways of biometric authentication. Let's talk about how we analyze the usability of those inputs. So for voice recognition, the person has to speak their password, or like we saw in this case, a series of numbers. That has medium speed because you have to take the time to actually say the phrase. If we look at that example that I did and showed you on my iPhone, it took me a lot longer to say those numbers than it would have to just type something in. However, typing in a long password, for example, might have enough errors or just take long enough to get right on the keyboard that it would take longer than the voice recognition. So we're going to say the speed's about medium. The efficiency is also medium. Here we're looking at the number of errors that a person can make. If you use a very different tone of voice than you normally do, so if you speak high, if you have a cold, the voice recognition may not actually recognize your voice. And so there is a decent chance for error. This can also happen not because of anything with the user's voice, but if you happen to be authenticating in a noisy room or somewhere where there's a lot going on in the background.
7631.
However, it's quite easy for people to learn to use these systems. In fact, they're generally prompted to do what they have to do. And the memorability is quite easy. You don't really have to remember anything because the system prompts you with what you're supposed to do. The only thing a person might have to remember is a passphrase. That wasn't the case in the app that we looked at, but that could be something that may be a little bit difficult to remember, depending on the user. Facial recognition also has a medium speed. It takes a little bit of time for the system to actually pull up those points and recognize your face. It has medium efficiency. Depending on the lighting situation you're in, it's actually possible that the system won't recognize your face. Learnability is easy. All you have to do is put your face in front of the camera, and memorability is also easy. Fingerprint recognition is quite fast, as we've seen in a few videos showing the fingerprint login for the iPhone. The efficiency is good. It could be that you get in the wrong position and it's difficult for the system to recognize you, but generally, as someone who's used these systems for quite a while, it's unusual that there's an error that keeps me from logging in. Learnability and memorability are both easy. You just stick your thumb or your finger on the pad, and that's all you need to remember to do. But let's talk about analyzing the security of these systems, because that's something that is a little bit more complicated. We need to look at who can access the device. So if we're talking about somebody breaking the biometric authentication on a mobile device, they first have to get access to your phone, and that's actually a big security barrier on its own. On the other hand, if you're talking about using this kind of authentication for remote login to a system, then potentially anyone with internet access can approach the computer or the system and try to authenticate themselves. So that actually makes a big difference in the security of these authentication mechanisms. This is something that we can see in other arenas too. You probably wouldn't use a 4-digit PIN as your online password for your bank, but you would use a 4-digit PIN to log in on an ATM because you also have to have the card with you. Similarly, you would use a 4-digit PIN on your mobile device because it's something that you keep with you, and it's hard for a random attacker to gain access to it. we also want to look at how easily they can replicate the biometric input. You certainly see examples where people are able to trick thumbprint recognition systems with something like a 3D printed thumbprint. In some systems you can even do it with a photocopy of a person's thumbprint. But to do that, they need to get a copy of your thumbprint. That makes it difficult to replicate the biometric input, even though it may be easy to trick the biometric recognition system once you have the thumbprint replicated. Similarly, you may be able to get recordings of a person's voice, photos of their face, or pictures of their eyes that you could use to trick a system. But again, getting a person to say the right thing, or getting a photo that's in the right light, or that has enough detail on their eyes is difficult. So replicating biometrics is actually quite hard. And you hear discussions about the security of biometric systems being low because it's easy to trick the systems once you have the biometrics replicated. But that ignores the fact that it's actually pretty difficult to replicate biometrics. So to wrap up, we can see that biometrics are easy to use and they're relatively secure, especially because they're common on mobile devices. Even though it's possible to break them, it's difficult to replicate biometric information, and often you need to have the device because they're very common on mobile devices. When you analyze usability, we did a quick high-level look at speed, efficiency, memorability, and learnability, but you really need to do comparative usability. How easy are these to use in those 4 ways, and including user preference, compared to PINs and passwords? How well do they protect security is a question that should go along with this, but you want to think about what users are going to do. If passwords are too hard for them to use on mobile devices, they may just turn off security on the device altogether. So you need to look at the usability of these authentication mechanisms compared to one another, and then think about what kind of security options they offer as well. In this lecture, we're going to talk about gesture-based authentication. This can be related to biometric authentication, but it doesn't have to be. So we're going to start by looking at a couple different types of gesture-based authentication and then talk about the usability of these systems. First, keypad gestures are a type of gesture-based authentication where users are given 9 points, usually laid out in the form of a keyboard, and they're asked to pick a gesture that connects those points together in order to authenticate themselves into a system. This is a type of gesture-based authentication that's commonly used in Android systems, so some of you are probably familiar with it. Let's take a look at those types of gestures in use. Here you can see we're being prompted to create a gesture-based password with these 9 points on the Android. So when I get started, I can pick a pattern. This one looks sort of like an N. Once I've decided on it, I'm asked to repeat it to confirm, just like we would with any password. And now it's set. So if I turn the device off and turn it back on, and I'm prompted to log in, if I put in the wrong password, it doesn't work. If I put in the correct pattern, I'm authenticated. There are alternatives to this kind of controlled gesture that bridge the space between keypad gestures and free gestures. In those cases, instead of having a keypad, you may have an image, and you create a gesture linking different faces or different points in the image. Free gestures don't require any kind of background at all, and we'll take a look at a few examples of those. In these cases, a person picks whatever kind of gesture they want. It doesn't have to pick any particular point, and the computer learns to recognize that gesture. These are biometrically based because even if someone else comes in and tries to do the same gesture, there will be subtle differences in the way 2 people enter it. Pictures lie in the middle of this space because essentially you're looking for people hitting the same point on an image. That's not necessarily biometric, but totally free gestures are. So let's look at a few examples of those. In this example, we're looking at a freeform gesture system. I'll have a link to the full video of this below. A user is asked to create a gesture, in this case it's a capital L, and they input it a bunch of times. Once the system learns it, they can authenticate by entering that same gesture, and the system lets them in. This is biometric because if someone else comes along and tries to log in, they've looked over the shoulder, they try to draw the same figure, the system actually keeps them out. This next example allows users to enter a signature. So we'll see the phone rotate here so we get a better perspective on it. You can write this however you like, and you have to go through a series of training examples, just like in the previous case. Notice that the alignment of these letters, the size, is different in each case. So the user who's creating this authentication mechanism does their signature 5 different times. There are slight differences every time, and that's okay because there are going to be differences every time a person goes to enter it. Once they've done their 5 logins, they can then actually try to log into the system, typing the phrase, and then it works. Finally, here's an example using multi-touch, where a user makes a gesture with all 5 fingers that the computer trains on, as we see with multiple examples here, and then the user can use it to log in. In all of these examples, we're looking at free gestures where users can create whatever gesture they want on the screen. The system has them repeat it a few times so it learns the variations in how they enter it, and then that becomes the way they authenticate. It gives users a lot of freedom, but it's also actually quite secure because there are small differences between how each person would enter the same information, and the computer can pick up on that, so there are biometrics built into recognizing these gestures. Now, what about the benefits of doing gesture-based authentication? It's interesting, but is it usable and is it secure? What research has shown is that gestures that users enjoy creating and using, which means users think they're easy to use to log in, they're fun to create, and so on, those user-preferred gestures tend to be the more secure gestures. The things that are boring and that users don't like inputting, that maybe are hard, also tend to be less secure. And so there's a nice parallel between user preference and security. Users prefer using gestures over using actual passwords, and that's because it's easier to use a gesture, especially on a small mobile device, and it's easier to remember in a lot of cases. And finally, gestures are faster than passwords and they're less error prone. So we have user preference, speed, and efficiency all working towards usability. And we have these additional results that show gesture-based authentication also tends to be more secure. So this is a real win. In the next lecture, we will look at an example of gesture-based authentication attacks, which I think is an interesting take on what we normally think of as someone breaking into a system. So let's take a look now at a case study we're doing on a paper that has been assigned to you on smudge attacks. The paper is by Adam Aviv, and in the next video we'll actually see an interview with him. For now, please read the assigned smudge attacks paper that's linked in this week's page before you get into this video. So smudge attacks are attacks that take the fingerprints that a person leaves when they do a gesture-based authentication on a mobile device, and it uses those fingerprints to identify what their gesture-based password is. Let's take a look at one of these mobile devices just to remind ourselves of what these passwords should look like. So remember, this is my Android device, and I was able to create this 9-point gesture-based password in the shape of an N, and we saw that in a previous video. In this paper, the researchers were concerned with identifying whether or not these smudges could be seen and how much information that gave about passwords. They did a setup where they had lighting sources at a few different angles and a camera, and they would use that to take pictures of the screen. Here's an example of one of the phones from the study, and you can see pretty clearly from this picture that you can pick out where the fingers went when they stopped and what paths they followed. And just so you can see that this wasn't their researchy prototype making it look worse than it actually was, here's the device that I've been using, and if you remember, I had set up a gesture-based password on this. In this picture, I'm just holding it in front of the window, and you can see the N-shaped pattern of my password pretty clearly. If I tweak the image a bit, increase the contrast, and adjust the exposure, that becomes extremely clear, and this is something a computer could do quite easily. So the researchers used multiple phones in their study. They had 2 phones that started off clean. One, the password was entered with a normal touch, and on the other it was entered with a light touch. They also had a dirty phone that had smudges from being held up to someone's face as though they had been on a call. So that would get some oils from the face and potentially other fingerprints on the phone, and then the password was entered on top of that. What did they find? Not too surprisingly, it was pretty easy to retrieve at least some information about passwords from those smudges. The clean phones obviously worked better, and as we saw in the photographic examples, you can pull a lot off of a clean screen with some good lighting and a camera. The dirty phones were less easy to pull information off of, but even on those very dirty screens that had been touching people's faces, that had been handled and not cleaned, they were still able to pull a lot of password information. So they may not have been able to see every finger touch and path that was followed, but they could see a lot of it, and that would be a good step towards actually retrieving someone's password. So in conclusion, this paper shows an interesting attack on non-traditional authentication. Normally, when we think of someone breaking into a secure system, we either think of them hacking or cracking the password, or maybe circumventing the authentication system altogether. In this case, we have a human-based password attack with a twist. It's not humans socially engineering one another to ask for the password or guess it or find where it's hidden. It's doing some analysis that requires a little bit more sneakiness than we normally think of with human attacks, and a little bit of analysis in order to recover password information. It's also pretty effective. And that's an interesting thing to look at, especially when we're used to thinking of combinatorial issues with respect to the types of characters that appear in a password. That's not to say that gesture-based authentication isn't secure. As we've discussed in previous videos, someone still needs to gain access to your device, and once they get there, they need to figure out what your password is. This shows that there are ways for people to guess that, and it's just something to keep in mind when you're thinking about the security of a system and what ways you want to allow users to authenticate. In this video, we're going to see an interview with Dr. Adam Aviv. He's an assistant professor at the U.S. Naval Academy and an expert on usable security. He's also the author of the paper we read about smudge attacks.
So I purchased a Google phone when they first came out. I was very excited about it, and I put on this password pattern, and it was awesome. And then I started waking up every morning, and I would look at my phone, and I would see my password on the phone, just embedded there in the smudge. And I asked myself, well, I wonder how common this is, and under what conditions this would occur. And so I went to my advisor, Matt Blaze, and he was like, that's awesome, let's do it. And so we bought a bunch of photographic equipment, and we took a bunch of measurements, and we found that, yes, these things seem to be quite common. And using really off-the-shelf software, like anything that can affect the levels of the contrast, images where you didn't even think a smudge was present may actually have quite a decent amount of information in it. Even partial information could actually be used to recreate your password. Yeah, so I think the most surprising thing to me was that at the time, we had 2 types of technology for touchscreens. If you think way back for the G1 phone, was a plastic face versus the new Nexus models, which are the phones that eventually took over, were a glass face. And one of the things we wondered is whether or not there'd be a difference between the 2 form factors. And what we found actually is that the glass face was actually worse. So we're moving into a domain where glass would actually cause more problems than the plastic surface that was prominent at the time. Yeah, so that's a really interesting question. fact, it's a question I get asked often. So if you look at the literature in the graphical password, gesture-based password space, they always make this promise that they're going to be more secure than text-based passwords. They're going to offer more diversity in the choices that you can make, and that they're going to be more memorable because people are visual things and they can remember an image or a gesture or some sort of factor better than they can remember some random text, right? And this is going to be the future, and this is going to be great. And if you look at what actually happens in the technology, you find that no, these things don't seem to be used at all, which was really surprising for me when I was looking into this, that we actually did build a gesture-based system on Android, and the result of that is that they didn't think it all the way through in terms of actually how we're going to use that gesture on the device itself. And like figuring out how that interaction actually can degrade the security of the system was totally not really considered at the time of the implementation. And if you go even further down and actually study these things, maybe the gesture-based password on Android is not a great example, but it turns out to be actually less diverse than a lot of other systems that could have been put in place, which means there are smaller sets of patterns available. And even further research now suggests, some of my own and some of my colleagues, that people also choose terribly on these things, as terribly, maybe even more terribly than they do in text-based passwords. So it's a really interesting challenge because on the one hand, history is right. The researchers were right that all gesture-based passwords, graphical-based passwords are much better for humans, for memorability, and a lot of other things. But if you look at it actually how it gets implemented, it doesn't always work out the way we plan. So if you actually look at what's happening out there right now, we're not doing this. And I think it's more interesting to ask why we haven't done this while we clearly can. For example, using our fingerprint biometric on iPhones is a really common thing on our laptops to unlock the current device that's in front of us. But these things are not necessarily used for remote authentication. And one of the reasons is that most of the biometric stuff that we have out there is not actually that secure. People have shown that you can use Plato to thwart fingerprint analysis, and actually doing this as a secure way of logging into sites just doesn't seem to have latched on in the community of people who have developed this. And I think that's probably because they haven't seen it as a actual secure choice the way we want to. That hasn't stopped researchers like myself and to think about these problems and what would that mean, and we try and think about it all the time. But in the end, if we can't come up with something that's actually strongly secure based on devices that are commodity that are available for everyone to use, it's never going to really catch on.